Hello everyone. Our speaker today is Noa Fruchter. Noa completed her master's studies at the Hebrew University, working on the quaternary drainage system evolution in active rift margins. Noa completed her PhD at Geomar Kiel at Germany, working on Strontium Calcium Isotopes as a tool to study coral calcification mechanisms under supervision of Professor Anton Eisenhower. And today Noa is a postdoc working at the Geological Survey of Israel in cooperation with Hebrew University, while the work focuses on the calcite precipitation process in Lake Kinneret using strontium and calcium isotopes. Please.
Hi. Okay. So thank you. Okay. So I'm going to present to you today part of my work that I'm currently doing as a postdoc. I started that about a year ago. And I'm going to present you some initial results from the calcite precipitation process in Lake Kinneret and the results of strontium isotopes. Now this work is with cooperation of several people, including Moti Stein, Boaz Lazar, Ami Nishri, and Ahuva Almogi. Now, Lake Kinneret, as you probably know, is a freshwater lake. The pH of the water is always is above 7, and in some periods of the year it becomes even more alkaline, as it becomes about 9.5 maximum. These alkaline conditions are one of the reasons why spontaneous precipitation of calcite occurs in Lake Kinneret, especially when the conditions are getting more and more alkaline. And this calcite accumulates as sediment in the lake's bottom and kind of creates an archive of the calcite precipitation history. The formation of calcite in Lake Kinneret is biologically induced mineralization, and these algae, especially the pyridinium algae that do photosynthesis, are causing conditions that leads to this calcite precipitation. So specifically, what happens is that carbon dioxide together with some nutrients are taken from the water to create organic matter. And during the spring, these algae do what is called algae bloom. And in this process, massive amount of algae do massive amount of photosynthesis, and this actually alters the composition of the water. And one of the things that changes in the water is the pH. The pH increases in the water. As a result of the pH increase, there is a shift in the species of some elements in the water, including the dissolved inorganic carbon. So the dissolved inorganic carbon, when the pH increases, shifts toward higher concentration of the ionic compounds of this dissolved inorganic carbon, including bicarbonate and carbonate ion that increases in their concentration on the expense of carbon dioxide. And these species are the species that are available for the precipitation of carbonate minerals, including calcite. And actually this is what happens. So algae bloom, they increase the pH of the water, and then they cause an increase of the saturation state for the precipitation of calcite in Lake Kinneret. And this calcite precipitates in large amount, and then and it's especially happening in the upper part of the water where the algae bloom. So as I said, it's biologically induced precipitation, and it's very local. It happens in the upper few meters of the water, and this calcite then sinks to the bottom of the lake and accumulates there as a sediment. So you can see indeed that in the springtime there is an increase in the calcite saturation state. There is a massive increase. We get to 22 level of saturation state, where above 1 is oversaturated. And it is also similar to the pH. The pH increases because of the algae bloom, and it especially happens in April and May. And also the consuming of silica is together with it, because one of the algae that bloom in Lake Kinneret is diatoms, that takes silica from the water. So you can see that all of them together are kind of happening together, and it's kind of a circle. So both calcite precipitation and the biological photosynthesis have a major role in this carbon cycle and the carbonate system of this aquatic system. And also the kinetic of all these processes of, let's say, the precipitation rate of the calcite is influencing and is being influenced by this carbonate system and by the carbon cycle, especially the exchange between the atmosphere and the aquatic system of carbon dioxide. So I can divide this project into two parts. Currently, I'm still working on the first part. And this first part is actually calibration. I'm working on the current system in Lake Kinneret, working on the calcite precipitation that precipitates currently, and I'm trying to understand the rates, the connection between the rates and the fractionation of 88 to 86 strontium. Later on, when we get a proper calibration, we go to the historical lake using sediment cores that were already drilled in the lake. We are going to try to reconstruct historical precipitation rate and to have some conclusions about the carbonate system, to understand maybe the history of, to reconstruct historical events that are related to this carbon cycle and to the carbonate system. So, I'm working on strontium. Strontium is an element that replaces calcium in calcite crystal. It has similar properties that makes it a good candidate to replace strontium in the lattice. Its distribution coefficient is 0.2, which makes it in Lake Kinneret about 1,000 ppm of strontium is in the crystal of calcite in Lake Kinneret. This strontium has 4 stable isotopes in nature. It includes strontium 84, which is the less abundant isotope, strontium 86, strontium 87, which is a radiogenic isotope, meaning that it is the product of the radioactive decay of rubidium 87, and strontium 88, which is the most abundant isotope. And you probably know this isotopic system, you probably know 8786. It is being used as part of the rock dating system of rubidium strontium. It is also being used for tracing sources of sediments or in the sedimentary environment. And when establishing this isotopic system of 8786, researchers had to overcome analytical fractionations. So in order to overcome it, 8786 was normalized to a constant 8886 number. And only later, so this number is actually the number of the, is actually the value of the standard of strontium. And only later, in 2006, Fitzke and Eisenhower, and also later Halich et al., including me in 2008, showed that 8886 is actually not constant. This number is true for the standard, but it is subjected to some changes in the natural environment. These changes are approximately in the range of less than a per mil, but they're still detectable and significant. So regarding these changes, to the results of 8886 are being displayed like oxygen isotopes in a delta notation. So the sample ratio is shown compared to a known standard, in this case this SRM strontium, SRM 987 strontium standard. And you can see here that the variation are indeed less than a per mil, but they're still significant, as I said, which this is the standard that the delta is compared to it. And you can see that different environments show different fractionation, and some of them show quite large variation in the fractionation. So pay attention to inorganic calcite, because this is the subject that I'm talking about today. It has quite a large variation. And on the contrary, corals and inorganic aragonite show quite a small range of variations in this fractionation of strontium isotopes. So, as I said earlier, when measuring strontium isotope, you see analytical fractionation. So the machine is doing fractionation, so you need to overcome it. And when you measure 8786, you normalize it to a constant 8886. But when you measure 8886 strontium, we're using what is called the double spike method. In this double spike method, we're using 87 strontium, 84 strontium mixed standards with a known ratio that then is added to the sample as a spike and is measured as part of the sample, and that's kind of an algorithm to correct the number and to get eventually the 8886 strontium value. The measurements are done on the thermal ionization mass spectrometry. It is done in Geomar in Kiel in Germany, where I did my PhD. And it was actually also measured in multi-collector ICP-MS, but it was found that this uncertainty is about 4 times this number. So 4 times this number, if we go back here, you can see that it's quite a lot of this range. So we're talking about almost 0.1. So it is something like this. This is the 2 standard deviation. And in the TIMS, we can measure 4 times better resolution than that. So as I said, Strontium isotopes are shown as delta notation, and for comparison reasons I will show sometimes the strontium isotopes as big delta, which is the delta of the small delta of the calcite compared to the water from which, the solution from which the calcite precipitated. Now, previous experiments that were done on calcite were done in laboratory, and calcite was precipitated in laboratory conditions, and there was found a kinetic correlation between the rate of precipitation of calcite to the strontium isotope fractionation. And actually, calcite prefers anyway the light isotope, the 86 isotope, over the 88. But as the precipitation rate increases, this tendency of taking the light isotope is increasing, and this is kind of a kinetic effect. But what you see here has been shown by Boom et al. 2012 and has been shown later by other studies, but it was never shown in natural environment. It was always done only in laboratory. So this is why we could choose Lake Kinneret as a natural laboratory. So this is bathymetric of Lake Kinneret, and most of our work is focused in Station A, what is called Station A. This is more or less the middle of the lake and the most
the deepest.
Yeah, the deepest, thanks. The deepest part of the lake. It is about 40 meters deep. And there we sample water, we sample parameters, we monitor parameters of the water, including pH, temperature, etc. And we also position sediment traps. So sediment traps are situated in the middle of the water column and are being taken from the water in order to collect the sediments every few days or weeks. So sediment traps, as I said, in the middle of the water column at about 20 meters. Last year they looked like this, very simple construction of sediment traps. It is just 60 centimeter long tubes, PVC tubes. At the end you have pipes, at the end you have tubes that collect the descending calcite. And this year I have built some traps that are actually better for marine traps. So the construction is more complicated and heavy to handle, but they still work. So this year we have something a bit different, but it's the same concept. And every, let's say, a week or up to 3 weeks, we collect the sediment, and the sediment includes calcite crystals like this, but it includes also other suspending solids. It includes skeletons of the algae that blooms there. It contains clays, it contains dust. And then the sediment is taken, we dry it, and after we dry it, we need to take the calcite only, because this is what we are interested. So we weigh the total weight of the sediment that was collected in the traps during this period. We dissolve the calcite using only acetic acid. This is how we guarantee that only the calcium carbonate dissolves. And then we extract the solution, we measure calcium concentration, and from the calcium concentration we can know how much portion of calcite there is in the total sediment. So that's the way actually to afterwards to calculate the rate of precipitation. So actually what we do is we take the amount of calcium carbonate that was trapped in the sediment and divide it by the days and the area of the trap. And theoretically speaking, the rate of precipitation is correlated to the saturation state, the one that I showed you earlier that is getting up to 22 in this springtime. But so in theory, we can say that there is a correlation between rate and saturation state, and the saturation state is a product of, not a product, is a result of the ion product and the temperature of the water. But these other parameters that exist, in a natural environment, they are hard to control. Actually, impossible to control them, and it is impossible to control them, and actually very hard to monitor some of them. So, as opposed to laboratory experiments where it is really as opposed to laboratory experiments where it is really easy, more or less, to monitor it, and then the rate is almost linearly correlated to the saturation state. In natural environment, we are not expecting it. So the presence or the absence of condensation nuclei can cause precipitation or non-precipitation even in very, very high saturation state. And the surface area, just as a comment, when you do laboratory experiments, the surface area is being replaced by this, so that the rate is not calculated by the area of the vessel where you do the experiment. It is being calculated by the surface area of the crystal itself. And it is not possible in a natural environment, because in a natural environment you can't take out the, let's say, the clays that sticks to the crystal, and they have a very, very large saturation, a very large surface area, sorry. Okay, so this was just actually a comment. Now regarding the results, 88, 86 was measured, the rate was calculated like I showed you, and we have, again, this negative correlation. So as the precipitation rate increases, the fractionation increases, meaning that the calcite prefers more and more the 86 over the 88. Now, 2014 was, in a lot of parameters, very different and very low in precipitation, also very low in this algae bloom, especially of this peridymium bloom. So we're talking about an average of 2 grams of calcite per square meter per day, with a range between 0.2 to 6 grams per meter square per day. And this is the period between March and July, which is including the period of the peak of the precipitation. And literature actually is talking about much more, much higher precipitation rates. Literature is talking about between 10 and 20 grams per meter square per day. So we actually continued this year to put sediment traps and to continue this calibration in order to extend this calibration curve and to see how is it in higher rates. I don't have the result of this year yet. It's just the beginning, but as it seems for now, it seems like this year is not better than last year. So I'm probably will not be expecting for higher rates than what we see here. Just for comparison, As I said earlier, the square meter is not measured in the same way in the laboratory experiments and in the natural environment, but just to show you that the laboratory experiments by Boom et al. 2012 is very similar, at least in the trend, to the current system, meaning that a natural environment is showing the same trend and more or less surprisingly actually similar results as laboratory experiments. So I actually showed you this connection between fractionation and precipitation rate. But in the current system, we measured the water, we measured the sediment, and we correlate this, which is the fractionation between the water and the sediment, to precipitation rate. But when we have different water compositions, we have different fractionations. And the fractionation itself is the one that is correlated to the precipitation rate. So when we don't know the composition of the water, let's say in historical time when we go to the sediment core, we need, in order to reconstruct the rate of precipitation, we need actually to know the fractionation, the amount of fractionation, the difference between the calcite and the water. So we need to reconstruct the water composition. So for that, first we know that the isotopic composition can change. And it is necessary to reconstruct precipitation rates because otherwise we will get false rates of precipitation. So how do we reconstruct 88, 86 of the water? So earlier I showed you that aragonite, I worked on corals and inorganic aragonite in my PhD, but the assumption that I do now is that every aragonite crystal has a constant fractionation. The range of variation is very, very small, almost not detectable. And previous studies show that there is no environmental effect, meaning temperature, rates, pH, nothing influences the isotope fractionation in aragonite. So we assume that it is maybe the same also in Melanopsis shells. Melanopsis shells lives in the shores of Lake Kinneret. They have lived in the shores of Lake Kinneret also in ancient times, so we can find them in the sedimentary record. And we say that if we measure this isotopic composition of the Melanopsis shells, we can reconstruct, by knowing the amount of fractionation, we can reconstruct the historical composition of the water. So actually this describes it. We have a constant amount of fractionation, which we can calibrate in the current lake, and then we can reconstruct the composition of the water based on this constant fractionation. So up to now I took Melanopsis shells from only 3 different sites. One is Fulia Springs. It is saline springs in Lake Kinneret. This I gave a name to a shore next to the tomb of Meir Balanes. It's in the kind of west-south part of Lake Kinneret. And Sapir Station, which is where the Kinneret laboratory is positioned. I measured the Melanopsis shells. I measured the water from which the Melanopsis were taken. It was living Melanopsis, of course. And you can see that there is quite large variations. We have minus 164 in Fulia, and in Sapir we have minus 220. It is significant variation. So at the beginning I thought, okay, maybe it is not constant. But then I said, okay, I will measure 87, 86. As I said earlier, 87, 86 is a tool to detect sources. So it means that if the Melanopsis was precipitated from the water, the composition of the water and the Melanopsis have to be the same. Okay, so the Melanopsis in Mayo-Balanese site, perfect. This is the water is underneath. The Melanopsis in Sapir is also okay. But the Melanopsis in Fulia is showing similar composition as the lake. But the water from which I took the Melanopsis is very different. It's a saline spring. So my conclusion up to now is that probably this Melanopsis from Fulia area was calcifying its skeleton from Lake Kinneret water. And actually, afterwards I found out that it's not a perfect site because Fulia is full of springs and groundwater, and also some Lake Kinneret water that are very close to there. So probably these Melanopsis that I took were just landing in this spring that I sampled them from, but they were probably living and precipitating their skeleton from other water than this. It couldn't be otherwise. So if I now take the water of Lake Kinneret and the Melanopsis, I get more reasonable numbers. Now I have smaller variations, which are very similar to the smaller variations that I saw in corals and in inorganic aragonite. So the conclusion from that is that I still need to do some more measurements of some other Melanopsis in order to establish this theory, but more or less it is going to the right direction, I think. Okay. Now, the lake composition. The composition of the lake, I will show you first the 87-86 results. So according to the 87-86 results, I took some sources that contribute strontium to Lake Kinneret, and these sources are mainly the saline springs and the Jordan River, which is represented here as in the sample of algae bleach. And I did kind of a mass balance of this mixture between the saline springs and Jordan River. And Lake Kinneret is sitting in between them. So according to the current study, when I do this mass balance, the saline springs contribute most of the strontium to the lake, 65% actually, and only 35% is coming from the Jordanian River. Previous work, like Kolodny et al., Kolodny 1999, showed higher contribution from the saline springs and much smaller from the Jordanian River. And other studies I took, as an example, Rimmel and Gall in 2003, they showed only discharges. So I had to add my measurements of strontium concentrations, and they got quite a large range of between 60 and 70% of strontium contribution from the saline springs, and about 40 to 30% from the Jordan River. And the result of the current study seems to be in agreement, or at least in the range of these Rimmer and Gall results. But when I add the 88-86 results in kind of a 3 isotope plot, you can see that there is this mixture line between Jordan River and the saline springs, but Lake Kinneret is not sitting in this mixing line. Lake Kinneret is deviating toward heavier isotopic 8886 concentration. Heavier, meaning that it could be that the calcium carbonate precipitation, which is ranging here, may have changed the composition, the 8886 composition of the water, and therefore causing heavier composition of the water. So actually it was trivial, and many have asked me if I can calculate the amount of calcite that precipitates, meaning the deviation between the lake and the water. And I just wanted to add that these water measurements are in the period of high precipitation in between March and June. And when I calculate the amount of deviation, from the amount of deviation, the amount of calcite that's supposed to be precipitating, so this is kind of very tedious calculation, but basically it is taking the upper 15 meters of the water, and this is the amount of water that there is. With the concentration of strontium in the lake, we get 1.6 million kilogram of strontium that exists in this column. And we do this math of what is the mixing line between the sources minus the amount of calcite that precipitates, not the amount, the composition, the isotopic composition of the calcite that precipitates, and this is the composition that exists in the lake after the precipitation. And from that we get to this number, which is 348,000 ton of calcium carbonate that precipitates in the lake. I don't know if it says something, but wait, okay, so I don't know if it says something, but in Lake Kinneret, actually, Nishri and Stila in 2014, and actually monitoring of other researchers there, shows about 5 times less precipitation of calcite in a year. And why do I say a year? Because I thought that this measurement in September of the lake says that the system resets, and that this is the composition of the water during the spring when the precipitation is massive, but during this off-season period of precipitation, the system resets and it tends to go back to this mixing line. But since we got 5 times overestimation, it can be explained by either one of these things. Maybe the system does not reset each year. Maybe the high measurement uncertainty just show me this large deviation. Maybe it's not so large. And another possibility, which is also very plausible, is that there are other strontium sources to the lake that I'm not taking into consideration. Maybe the eastern springs have a major contribution to the lake strontium composition. And actually that's it. So I said that we showed here that 8886 can be used to estimate the rates of calcite precipitation. We can use Melanopsis shells to reconstruct the composition of 8886, but I still need to do some more sampling and to verify this hypothesis. And using that, based on knowing that and this calibration curve, we can go to this historical lake, to the course, and to reconstruct the historical precipitation rates of the lake. Okay, we saw that the precipitation changes the water composition and maybe changes the water composition towards the heavy composition. And currently it seems like 65% of the strontium in the lake comes from the saline springs, whereas only 35% comes from the Jordan River. The outlook regarding at least this Lake Kinneret project is, first, as I said, we need to measure other years. First, to see if we can extend this calibration curve, if we can have higher precipitation rates. This year we also put a sediment trap in the bottom of the lake, close to the bottom of the lake. Then we want to see the effect of dissolution of 8886 in the sediment. We want to make sure that dissolution does not affect the 8886, because when we go to the sedimentary record, we sample sediment that already precipitated and underwent some dissolution effects. So we need to make sure that it doesn't affect the composition of 8886. Of course, more sampling of Melanopsis shells is definitely needed. And then we will go to sediment cores, first with the Holocene, because we have sediment core of the Holocene in Station A, where I put the sediment traps, and later on we can go to more ancient cores, like the Pleistocene in the, I forgot the name of the site. Wait. Never mind. Okay, that's it.
Thank you very much, Noa. Any questions, please? Yes, please.
Me first? Okay. Okay, so a couple of questions. I'll start with the most rudimentary one. How come you're precipitating you have chemical precipitation of calcite where most lakes don't precipitate calcite, they precipitate aragonite?
Most lakes? You mean?
In most, or at least saline lakes that I'm aware of. Why is calcite being precipitated instead of aragonite?
Well, I don't know. You are talking about what, soda lakes and others, or first because I mean when the precipitation, when the saturation state becomes so high, you need other conditions, of course. But if you have the other condition like condensation nucleus and the composition of the water, you need to have the element composition that does not inhibit precipitation, because you have also some molecules that inhibit precipitation and some that encourages precipitation. There are other lakes that precipitate inorganic calcite, but I don't know of any saline one. I know of another freshwater lake in Turkey that precipitates inorganic calcite.
Okay, and the other thing is you calculated the calcite precipitation rate from the strontium isotope, but your basic assumption.
No, I didn't calculate the calcite precipitation rate of certain strontium isotopes.
The sum of calcite being precipitated.
The amount.
The amount.
Ah, okay, yeah.
And now this is assuming that Lake Kinneret essentially has one outlet for strontium and whatever inlets you have. Do you see the same thing or have you looked at the same thing with calcium isotopes?
Calcium isotope, I still didn't complete my measurements because I'm still struggling with the multi-collector.
Oh.
So I don't have any output regarding calcium isotopes. I hope to see something similar, and together I hope to see if maybe we can reconstruct the saturation state, just to eliminate the other parameters that interrupts me. But repeat the question? I'm not sure I understood it.
Well, you don't have the data yet, so you can't answer that.
Just a simple-minded question about the quantities. If I understand you right, there should be about between 10 and 15 centimeters a year of calcite being precipitated at the bottom of the lake. Am I correct?
No. Some of it dissolves, not a lot, but some of it dissolves. We're talking about a total sedimentation of 2 meters per 1,000 years, but it is total. It is including also these clays and organic shells and diatom shells and etc. About 60% of it is calcium, is calcium carbonate. So
Because I just did, you have 348,000
this-
tons. Let's say it's 2 tons per cubic meter.
It's
And
it's 5
then you
times
divide by the
overestimated.
area of the lake, and you find out on average that you have a large amount. But if you say that it's only 2 meters per 1,000 years, now you're talking about something that is perhaps 1/6 of this. 1/5 to 1/8 of that.
Yeah, so I did this calculation because it was trivial to go from this graph to calculating it, because I say that this is a deviation from what precipitates, so maybe from the mixing line, and this deviation from the mixing line I can calculate. So I did this exercise of calculating it in order to see if it can give me an estimation, but it is 5 times overestimated. And then it can be either one of these 3 things that makes this deviation. It could be my uncertainty in the measurement, which is not so small, and it could be also that the system does not reset each year, and it could be also that I have other sources.
So you actually believe more than 80,000 tons?
Yeah.
How does the methanogenic system of the Kinneret affect calcite precipitation, if at all?
I didn't check it. The lake is monomictic, and in the hypolimnion, in the lower part of the lake, we have anoxic effects. And these anoxic effects, the immediate thing that happened is a drop of the pH. So some of the calcites dissolve, but also in these parts where these non-anaerobic areas conditions occur, there is no calcite precipitation at all. In the upper part, I don't know how it affects because I didn't check it. But I didn't check it and I have no idea, actually.
Okay, any other questions, please?
Yeah.
Yes.
Just a simple question. In your sediment traps, you said you dissolved carbonates with acetic acid, but you also have carbonate dust. So how did you separate the calcite that precipitates in the blood?
I didn't separate it. I mean, the hope was that I don't have any significant dust, carbonate component in the dust, but the way actually to verify it was to see that the calcium carbonate in the lake, the 8786, the one that detects sources, in the calcium carbonate is similar to the one in the lake. And the dust component, I didn't check it, but from other studies in this area, some of them are not published, we're talking about higher number. We're talking about the dust component that is sitting at least here.
Yeah, but these are measurements in the water.
These are measurements of the water.
Yeah, so you can't really compare them to the dust because the dust doesn't dissolve, doesn't contribute to the water component.
And even if it does, it will increase the water composition, and then you will see it also you will see its component also in the calcite that precipitates. So, that's it.
Okay, any other question, please? Okay, thank you very much now for your talk.